And hello everyone, welcome back to DWSim. So in the last video, we are actually talking a little bit about some of the methods of heat exchanger calculation, and I also reminded you some of the important notes to take for recycling. And then I suddenly ended the video. I think I pressed the finish button a little bit early, but all the content I needed to cover was already there. So in this video, I just want to talk about the shell and tube version of calculation, and probably want to go through some of the options, describe them for you so that it's not so intimidating. So for this video, I hope to finish this shell and tube exchanger rating. So I'm going to save this under heat exchanger shell and tube. Okay, YouTube demo 6. Okay, we'll replace it, and yeah, let's edit some of the shell and tube properties, go through them one by one. Okay, so the first section under the shell and tube properties here, okay, you will see this edit shell and tube heat exchanger properties. You will be able to edit a lot of things here. So we have, of course, two diagrams here for shell and tube heat exchangers, which are, I think, pulled from Wikipedia. Right, see, shell and tube heat exchanger. But I may be wrong, I could be wrong, but this definitely looks like a Wikipedia. Yeah, this is definitely a Wikipedia picture. It looks like it. So yeah, these are the shell and tube heat exchanger pictures from Wikipedia. As of 2022, DWSim 7 does not automatically update what your shell and tube heat exchanger looks like based on your design here. However, it is still useful to look. So you can see your shell and tube heat exchanger, your tube side fluid will flow outwards. So this is a single pass, they call it. So why is it pass, single pass? Because the tube side goes in, it goes past, the shell's tube side fluid goes in. Okay, it goes through the goes through all the so tube side fluid goes through all the tubes here, and then comes out. So the fluid goes one pass like that, one pass. Okay, so this is a single pass for the tube side because it only goes once through the length of the heat exchanger. Okay, whereas for the shell, okay, the shell is like this. Okay, the shell fluid goes in one pass, two pass, three pass, four pass, five pass. So it passes through the tubes like 5 times. So I guess you could call this the shell pass is like 5 times. So how does the pass work? Well, to force the shell fluid to go across the tubes, there will be these baffles over here that actually restrict the flow and force the fluid to go up and down. As you can see here inside Wikipedia. So let me use paint. I'm so sorry. Maybe paint's a bit better. So this is the front section, and I guess you can see things from a side view. Maybe the drawing will turn out really ugly, but okay. So picture you have a fluid from a tube going in. Okay, yeah, I'm not going to try this. Okay, so let's say you have. Okay, I'll just do it like that. Okay, you have a baffle that goes maybe 80-90% of the way through. So this one will be dark colored, so that when let's say your shell fluid is going in front of the baffle, so it will go something like that. I will use blue colored. So you go in front of the baffle, and it cannot pass through because there's this baffle down here that's blocking the flow. So it has to go all the way under the baffle and go towards the other side in order to go through. And that is what these baffles. Where's my mouse? Yeah, that's what these baffles are here for. You have to force the flow to go up and down through the tubes. So how many times does the shell pass through most, if not all, of the tubes? This is how many shell passes that you will go through. Okay, so at least this one is fine. Okay, whereas look at this one. There's a straight tube heat exchanger. There's a 2-pass tube side, 5-pass on the shell side. Why is it 2-pass on the tube side? So you can see here the tube's fluid flows in from the left. It goes through the length of the tubes one time. Then it goes through the length of the shell. It goes through the whole length of the tubes the second time. So goes through the length of the exchanger once, goes through the length of the exchanger twice. There's a 2-pass. Whereas this one goes through the width of the exchanger 1, 2, 3, 4, 5. So it's 5 times of passing. Okay, so okay, either it's 4 or 5 times. Let's see. So this is it says here on Wikipedia, most shell and tube exchanger are either 1, 2, or 4 pass on the tube side. This refers to the number of the times the fluid in the tubes passes through the fluid in the shell. Okay, so this is in a single pass heat exchanger, fluid goes through one end of the tube and out the other. So this is a single pass. This is 2-pass. Okay. Okay, they don't talk about shell passes here, but I'm guessing by the logic of the tube passes. Well, you pass through the the length of the exchanger, or the length of the exchanger once or twice, then it will be single or double 2-pass. Then for shell side, if you pass through the width of the exchanger 1, 2, 3, 4, 5, I think this is a 5-pass. I could be wrong. I'm just like so-called yeah, I could of course look in Perry's Chemical Engineering Handbook, but yeah, as of now this is my best estimate. Okay, but what I can say is whether or not this is a 4 or 5-pass thing, I think it's a 5-pass. This will actually be what the shell passes are talking about. Okay, so we can talk about shell passes. Alright, so this is 2-pass for tubes, 5-pass for shell. I think it's 5-pass. And 1-pass for tube, 5-pass for shell. So so you can see on the shell side you will have shell passes which you can configure over here, whereas on the tube side you are able to see how many passes per shell. Alright. Okay, so the other thing you will be able to edit is this thing called shell in series. So this one I'm not going to really touch on it, but it's basically how many of the same heat exchangers you can connect together end to end. So you're making the heat exchanger thingy longer, which I don't think really makes sense. Unless there's a specific reason to do it. So I'm just not going to go through it at this point in time. You can just leave this number as 1 unless you really have to do otherwise. Now, what is this internal diameter? Well, this assumes the shell and tube heat exchanger has a cylindrical shape, just like what you might see. But yeah, this just assumes the shell and tube heat exchanger has a cylindrical shape, and you have this sort of configuration. Okay, internal diameter 500 mm. Okay, it's a 500 mm internal diameter cylinder. There may be what do you call that? The shell insulation on the outside, whatever it is. Okay, that's to provide insulation and to prevent heat loss. Okay. However, of course, you are able to for heat loss. You just kind of specify it here. So, I mean, I don't exactly like the way this is done, because heat loss you have to kind of do it manually, which I don't think is really realistic at all. Okay, it's not realistic to me. So I don't like that, but yeah, okay. So here next thing here is this thing called fouling factor. As you know, the tubes sort of yeah, your liquid is going to be very impure at times, and then sometimes they're going to deposit some gunk on this heat exchanger because of impurities. Especially the thing is that when the hot fluid, when it cools down, some things that are more soluble at higher temperature tends to kind of deposit out, and it will cause some gunking and fouling, and that will tend to decrease the heat exchange efficiency. Some of that you will account for in the fouling factor here. Okay, this I will not go through in detail this video how to do it. Yeah, I myself have kind of forgotten, or yeah, it's been way long since I talk about heat exchanger fouling factors, or heat exchanger for that matter, so I'm just trying to scrape things off my memory, and if I remember them, then I'll put down the sources. But as for now, I just go through what I'm familiar with. Okay, next thing is this thing called baffle spacing, right? Baffle spacing. So, well, baffle spacing is how much width between adjacent baffles. So it seems that you don't, DWSim here, you don't specify the length of the heat exchanger, so to speak. You don't specify the length of the heat exchanger, but what you do is you define how many passes there are. Okay, how many passes there are will define how many baffles there are. How many baffles there are, that will determine your baffle spacing. Okay. Alright, so next thing is this thing called baffle cut in percent of diameter. So what is baffle cut? Well, remember we had this picture of you know, to force the fluid to flow down across the tubes. To force the fluid to flow down across the tubes, you have to put a baffle. But of course, what you have to do also is to leave some space at the bottom to allow the fluid to flow through. And maybe this length is what, 20% of the diameter. Okay, where the diameter is the whole length here. The full D is here, the diameter of the thing. So you are able to adjust this manually. You can put a 30% cut. So you can actually make this white space a little bit more, a little bigger. Of course, then the advantage, okay, the advantage to this is that it will allow the flow to go through the tubes a little bit easier. There'll be less pressure drop. However, the contact between the hot and cold fluid won't be as good. So there's a trade-off here when you do these baffle cuts. It is a trade-off of pressure drop versus heat exchanger efficiency. And in fact, of course, turbulent flow will tend to provide better heat exchange, heat exchanger, because it kind of minimizes this boundary layer. But having turbulent flow may also increase the or decrease the or increase the pressure drop. Okay, so there is some sort of trade-off here if you want to use turbulent flow or you want to force the fluid across like that. Okay, this is a very simple way. I don't know if there are more efficient ways of thinning out the boundary layer. I'll leave that to the theoretical people or the new inventors to design more efficient versions of heat exchanger. But for the conventional one, this is what I know. So this is what these things mean here for the shell side. Okay. Now for the tube side. Okay. For the tube side, we will have a lot of things again. Okay. We have a lot of things again. We have internal diameter, external diameter. Okay, so there will be, of course, enclosed tubes or pipes within this what do you call that? Within this shell and tube heat exchanger. Okay, the length, I guess you are able to define the length of length of the tube overall. Okay, so whereas for the shell side, you don't define the length, but you define the baffle spacing and all of this stuff. For the tube side, you do define a pipe length. Okay, and I guess you have to make sure, that the baffle spacing and the shell passes, right? So this is 250 mm or 25 cm. 25 cm times 4. Okay, that should give you about 1 meter, or at least 1.25 meters. Okay, for this tube length, this is 5 meters. It looks like yeah, it looks like let me think. Yeah, it looks like, this thing is a 5 meter length, so there will be like partial coverage of the shell and tube. Okay, but suffice to say, this length here, okay, maybe I should explain what I mean. I'm going to delete this, and I'm going to use this is much better. I always like the dark background. Let's pull this out a little bit more. Okay, so what am I talking about here? So I guess as with all shell and tube exchangers, there will be a length of a pipe. There will be the tubes inside, which will have an internal and external diameter, because this will be not a thin tube. There will be actual material or metal or PVC or whatever that's going over it. They will have a certain thickness, so that's the external and internal diameter. There will be the length of the tube, which looks like for single pass. For single pass, it's quite straightforward what this length means. But for 2 pass, I think the effective length you have to like times 2, or maybe this length is the total length of the okay, I'm going to assume this. This length should be the length of 1 pass through the shell and tube heat exchanger. Okay, 1 pass. So if 2 passes, if there's a 2 pass heat exchanger, this thing will be 10 meters. Alright, so now this is a it's a 5 meter long tube, and you have a baffle spacing of 250 mm. So let's do the fluid like so. Yeah, and it's assumed that the baffles are pretty thin. I don't even see any baffle thickness being put here, but okay, whatever. So let's say there's a bundle of tubes. Oopsie. Let's say there's a bundle of tubes, and then you have your first baffle, right? So and then of course you have your tubes and going on like that, and then this, if you want to draw to scale, these two things should be 250 mm. Okay, so the tube side fluid will go down here and you'll go up. Then there will be, remember we want it 80% of the way through. That's what we kind of define here. So this is a 1 pass, 2 pass, 3 pass, and I suppose 4 pass to go out. So there are like 3 baffles, 250 mm each. Okay, well, I guess this, I'll just put the arrow like that. So 1 pass, you'll be forced downwards by the baffle. Then you'll go up 2 passes, down 3 passes, up 4 passes. Okay, so there'll be 3 baffles here. Okay, 3 baffles here. Yeah, three baffles on the shell side. Yeah, the thing is that if you take a look at this this setup, there'll be at least four spaces of 250 mm. right? 4 spaces of 250 mm. So 1, 2, 3, and 4. Alright, 4 spaces of 250 mm. And the thing is that the the total length of the exchange area is like 1 meter, whereas the tubes are 5 meters long. So depending how you set up your shell and tube heat exchanger, you might not be getting fluid flow through or very efficient contact through the whole thing. So this is something I guess you have to think about it on your own and consider, because the whole length of the tube is 5 mm, but if you consider how many times on the shell side, how many times it passes through, okay, it's a 4 times you pass it through, and then 4 times you pass it through, and 4 times you pass it through, and then what happens? And then you exit out. That means the rest of the tube, the rest of the tube here is not getting contacted at all by the tube side fluid. So the rest of the tube, in fact, is kind of drawn out to scale. 5 meters, if you really want to draw it to scale, it will kind of go much further along this side. Alright. Okay, because this is 1 meter, there should be a few more meters of tube that are just not being contacted. Alright, so you have to be, I think you should be quite wary of this. You have to bear this in mind. Okay, to bear this in mind. Yeah, so just bear this in mind when you design that. Okay, so that at least there should be contact throughout the whole tube. You may of course want to leave some space towards the end of the tubes. Okay, you may want to leave some space towards the end of the like the inlet plenum and the outlet plenum. You might want to leave some space, I don't know, but just bear this in mind. You may not always be contacting the whole shell and tube thing. So instead of 1 meter, I should be able to reduce this to 2 meters. Instead of 5 meters, I should be able to reduce this to 2 meters. There will also be a fouling factor on the tube side. Okay, and for, I guess, calculation of friction factor, there will be some roughness as well, which plays an important role for turbulent flow, and that will help you determine some sort of friction factor from the Reynolds number. And once you have a friction factor from the Reynolds number, you should be able to get some Nusselt number correlation. Okay, I don't know what they use behind the scenes. I'm not going to touch it. So thermal conductivity. What's the thermal conductivity of the material of the tube? This assumes constant thermal conductivity, of course, which may or may not be true, especially when your temperature changes. But I guess you use an average here. Anything else you need to program it on your own using Python or some other thing. Okay, passes per shell. Okay, passes per shell we explained earlier. Okay, on the shell, on the tube side, this one is a 2-pass tube side, so it goes through one array like that and goes down the other array like that. Okay, so this is up to you to settle. So I'll leave that to you. Tubes per shell. Here we have 50 tubes per shell. Again, based on the internal diameter, external diameter, and of course tube spacing, we may or may not be able to fit in all the tubes into the shell and tube heat exchanger. You must kind of consider the diameter here. Alright, the diameter and the way the tubes are arranged. So let's just set some rules of thumb straight, important reminders. Internal diameter must be less than external diameter, obviously. Okay, or else it's just not physical, right? internal diameter must be less than external diameter, and external diameter must always be less than the tube spacing, or else the tubes will be touching each other, or even worse, they're like crossing each other, which again doesn't make sense. Okay, so these three must sort of go in order because yeah, that's the way things are in reality, right? So I assume you know heat exchangers at least well, and you know what shell and tube heat exchangers are, how they are designed. If not, you can go look at Wikipedia. There are some diagrams for you. Even these designs were from Wikipedia. So tubes per shell 50, tube spacing 70 millimeters. So that's the space between adjacent tubes. So I'm going to delete all of this. So yeah, you have space between adjacent tubes from center to center. Okay, center to center. It's a center to center spacing. So this is well, half a diameter. All right, half diameter, and of course from here to here, there's half diameter. Half diameter, and of course by the half diameter I mean outer diameter, not inner diameter. So so this circle is the outlet diameter of the pipe. All right, and between this there should be some additional spacing in between. So this center to center distance must be more than 2 half outlet diameters. So that's why I say again, you must have excuse me, enough tube. The tube spacing must be more than the external diameter. Okay, so that at least there's some fluid from the shell side that flows through. Next option here is tube layout. Okay, tube layout, there are a few tube layouts here. What is a tube layout? Now if you search the web, okay, you search the web for tube layout, you'll be able to see on ResearchGate there is this sort of well, uploaded by Mr. Sunil, it looks like Arjun Sunil. So this present work has been carried out to predict performance of shell and tube heat exchanger using CFD, computational fluid dynamics, and SYS13. And then this is a triangular arrangement. As you can see here, the tubes, the closest tubes can be arranged to form one triangle. So, okay, 1, 2, 3. Okay, so this is a triangular arrangement. So the closest tubes will form a triangle. Okay, so that is the closest tubes. There's rotated square, rotated triangle. Okay, I don't know what it what rotated means. Maybe it's just the orientation. I don't know how many degrees. Maybe it's 90 degrees rotation. Yeah, that seems to be the logical choice. I mean, why would you rotate something 20 degrees? Yeah, so rotate it 90 degrees. So instead of doing this way, maybe you have a triangular setup that goes this way. Okay, to me it doesn't really make a difference if it's rotated or not. Maybe it does make a difference to you. That's why this option exists. Okay, square is again a slightly different orientation, so it's literally 1, 2, 3, 4, and you form a square like that. And the shell spacing, the spacing between adjacent tubes, I guess will be this. Okay, the spacing. I think the spacing is here. Spacing. Is spacing. I should click elsewhere. I'm so used to GIMP. Okay, so I think the spacing is the sides of the square, if I'm not wrong. So that's the pitch. Okay. It's easier for a triangle because the pitch is the same no matter. The spacing between triangular in a triangular arrangement, no matter what tubes you are talking about, they are always the same. However, for this case, your shortest distance is just across the length of the square, but there's a longer distance here as well, which may or may not be the pitch. I do not think it's the pitch though. Yeah, I don't think it's the pitch, but and yeah, the pitch will be this tube spacing. Pitch is just another word for tube spacing. That pitch is the distance, center to center distance between the tubes. Okay, so by default, I think, of course, if you don't want to be confused, just use triangle, and this will make sure the tubes are kind of bundled together like that rather than like in a square. So yeah, whereas for square pitch, I think it's at the sides, not the hypotenuse of this right angle triangle. That's my thinking. I could be wrong, but it is what it is. The last option here is fluid in the tubes. Do you want the hot or cold fluid? Alright, do you want the hot or cold fluid in the tubes? So in real life, here's my thought. If you have a tube, I'm drawing a very simple shell and tube heat exchanger, counter current. So I have a tube on the outside, single pass, single pipe. Okay, so you have a shell and a tube here. Alright, if let's say ambient temperature is what, 25 degrees C, or maybe what's 25 degrees in C in F, maybe it's 84. That's my guesstimation. I'm not sure. Let me check how close I am. Or maybe, yeah, that's not the point. Maybe this is 80F. Let me know if my Fahrenheit and Celsius mental conversion really works. Now, let's say your ambient temperature is 25 degrees or 80F, somewhere around room temperature. Exactly how much, I don't know. And let's say you are trying to have a heat exchanger here. Alright, and let's say you put the hot fluid outside. Right, hot fluid outside. This thing is going at 200 degrees C, and maybe it exits at 100 degrees C, right? And this heat, of course, is very precious. You want to dump as much of it as possible into the cold fluid because that's where your energy is. Okay, whereas the cold fluid is here. Cold fluid is here. Maybe you want to, it should go the other way. It's a counter current. Maybe it enters in at 30 degrees C, leaves at 70 degrees C, right? For whatever, this is just an example. Now, if you want to minimize the heat loss, then this setup may not be the best. Why? Because not only is this what do you call that? This hot fluid, not only is it losing it to the cold loop, it is also losing it to the environment. Okay, there's a heat loss. There's heat loss to the environment. Okay, and the temperature gradient is very high. This is 200 degrees C, and you'll probably make the outer shell a very hot surface, and you'll lose heat to the environment very fast because of the huge temperature difference. And to sort of minimize this heat loss, you might need to insulate. However, if you switch the arrangement, right? If you switch the arrangement, over. Okay, again, very poor drawing, but this time, let's have the hot fluid flow through the tube, 200 C again, and then we target 100 C output, and then now we have okay, now we have cold fluid in the tube side. Okay, 30 C in, 70 C out. For example, what happens now? Okay, this cold fluid I mean, this hot fluid will have no choice. It will have no choice but to lose heat to the cold fluid, which is what we want. Of course, this cold fluid will lose heat to the environment. We may or may not want that. But you see, this surface here will be a much lower temperature, and the heat loss will be significantly reduced. Okay. I mean, of course, for cryogenic applications, you kind of have the reverse, right? So you want to store the maybe you will have the cold stream here. If let's say I have it like that, minus 200 degrees C to minus 100 degrees C. Okay. Oh. Okay. Never mind. Let's make it simple, and we'll not use so many diagram drawings. So let's say you have a hot fluid, and maybe it's 200 degrees C. Cold fluid, your average temperature, right? Maybe the average of the hot and cold temperature is 50 degrees C. So you want it such that the hot will be in the tube, the cold will be in the shell, and then ambient is outside. So ambient, maybe it's 25, 70, or maybe we have 50, 200. So you can see that when we talk about the shell, the tube side, the tube side will have the highest temperature will have a higher temperature difference compared to the environment. So so the environment will be like the lowest temperature. You have the shell side, then the tube side will be at the top. So basically, if you want to prevent this heat loss, parasitic heat loss, you enclose the fluid with the greatest temperature difference with the environment. You put it in the shell, you put it in the tube. Then the fluid with less temperature difference compared to the environment, you put it in the shell. Okay, and of course for cryogenic applications, again you do something similar as well. But anyway, this video is not supposed to be about this, but let me keep my focus. I think I've gone too much into there. Okay, so fluid in the tubes, is up to you whether you want to put a hot or cold fluid. From a physical perspective, you can think about it based on what I said. You want to make from a physical perspective you can think about it, but over here in DWSim, it allows you to place either hot or cold fluid into this tube site, and sadly it doesn't auto calculate your heat loss for you. You have to do it yourself. So again, this is not so-called strictly speaking realistic, because depending on your average temperatures of the stream and everything, your heat loss rate will again differ, right? Your heat loss rate will differ based on the surface temperature of the shell and tube heat exchanger, how good your insulation is, blah blah blah. Right? So of course you want to minimize this as much as possible. Okay? So this will play a role. Unless you put a lot of insulation, you assume there's a lot of insulation so that heat loss will be negligible, then all this manual calculation of heat loss to an environment, you should not have to worry about it. Right? So I guess the assumption here is that your shell and tube heat exchanger should be very well insulated, so that no matter what, your maximum or your minimum heat loss, it will be kind of negligible to your whole operation. So that's the idea here. So this is the shell and tube heat exchanger rating. For fouling factor, you will be able to try and change your inlet and outlet fluid temperature, and then of course the options here are almost exactly the same, But instead of everything else being fixed for you, you are able to alter your hot and cold fluid outlet temperature. So that's a different mode of calculation. I would say if you want, if you already know the structure of your heat exchanger and you can assume a fouling factor, then you use the heat exchanger rating method. Then this will calculate your overall heat exchange coefficient for you, and then it should be able to do all the calculations for you and calculate the outlet temperatures, calculate the global heat exchanger coefficient, etc. etc. So based on this, I have air in at 25 degrees C, I have air out at 29.01 degrees C. It will calculate the hot fluid pressure drop and cold fluid pressure drop accordingly. Global heat exchange coefficient 25, heat loss 0.5 kilowatts. I mean, you can even set this to 0 if you want. Yeah, whatever like so-called makes sense to you. Okay, you just give a estimated value and you cross your fingers and hope it works. Yeah. All right. So that's up to you for the engineer to decide what's a suitable value for this heat exchanger. But yeah, that's all I think for this shell and tube heat exchanger design. So this is a more rigorous way of designing your heat exchanger, assuming it's a shell and tube. Any other configuration doesn't really work out as well. For that, you will then of course have to manually calculate the what do you call that, heat exchange coefficient for yourself, and yeah, and that will of course depend largely on your flow conditions, and that means your mass flow rate and your Reynolds number, Nusselt number, etc. etc. So all of this you have to take into account. Okay, that's why I would of course rather that DWSim does it for you. Now I don't exactly know what equations are going on behind this thing, behind the scenes. So you just have to assume that this is accurate enough. If you want to know what goes on behind the scenes, you have to go and see the source code. But that's another topic for another time. I may or may not make a video on that. Okay, as of now, I don't know how to do it yet. Okay, thanks for watching. I'll see you again.